Message queues. Imagine it's a Black Friday on Amazon. Millions of users are placing orders at the same time. Every order triggers multiple activities. An order confirmation email must be sent. An SMS notification must be sent. Inventory must be updated. Analytics must be recorded. Recommendation must be refreshed. Fraud detection system must be notified. Now imagine Amazon tries to do all of this immediately while the customer is waiting. What will happen? The website becomes slow. Orders take longer to complete. Customers get frustrated and eventually the system starts breaking under the load. Engineers faced this exact problem years ago and the solution they come up with become one of the most important building block of the modern distributed system. That solution is called message queue. Today we will learn what a message queue is, why it exists, how it works, producers and consumers, queue processing, real-world examples, trade-offs and frequently asked interview questions in this area. And by the end of this lesson, you will understand why almost every large-scale system uses message queue. Now let's see first what are the problem before. Let's revisit synchronous communication. Let's follow the request. A customer places an order. The order service calls the payment service. After payment succeeds, it calls the email service. Then it calls analytics service. Then it updates inventory. Notice what's happening. Every service is waiting for another service. The entire workflow behaves like a chain. If email service becomes slow, everything behind it becomes slow. If analytics crashes, order processing may fail. One service can affect the entire system. This architecture works when traffic is low, but at scale it becomes dangerous. At some point, engineers realize something important. Why should services talk directly to each other? Why not place something in between? Something that can temporarily hold work. Something that allows services to operate independently. Think about a restaurant. Customer places order. The chef doesn't immediately start cooking the moment one order arrives. Instead, orders are placed in an order queue. The kitchen processes them one by one. The queue acts as a buffer. And that's exactly what a message queue does. It acts as a buffer. Now what is a message queue? A message queue is simply a temporary storage area for messages. One service places message into a queue. Another service processes them later. Think of it as a mailbox. You drop a letter into the mailbox. You don't stand there waiting for the mail carrier. Eventually the letter gets delivered. That's exactly how message queues work. Now the basic architecture of message queue looks like this. Let's understand the simple queue architecture. At the top we have a producer. The producer is simply a service that creates messages. Maybe it's an order service, maybe it's a payment service, maybe user service. The producer generates some work and places a message into the message queue. Now notice something important. The producer job is finished. It doesn't wait. It doesn't care when the message is processed. It simply hands off the work. The message queue stores the message safely. Then later, the consumer picks up the message and processes it. This separation is what makes queues so powerful. Let's make this term crystal clear. Producer creates messages. Example, order service, payment service, user service. Consumer is someone who processes messages. Example, email service, analytics service, notification service. The producer produces work, consumer consumes work. That's why you will hear this term constantly when discussing message queue. Now for the Amazon example, let's walk through this architecture. A customer places an order. The order service receives the request. Payment succeeded. The order is confirmed. Now instead of directly calling multiple services, the order service creates a message. Something like order 123 created. The message is placed into a message queue. At this point, the order service is done. The customer immediately sees order successful. Now the queue takes over. The email service picks up the event and sends a confirmation email. The analytics service records business metrics. The inventory service updates product stock. Notice that all these services operates independently. Even if the email service becomes slow, inventory can continue working. Even if analytics crashes, orders still succeed. This is one of the biggest advantages of message queue. Now, why queues improve scalability? Let's imagine a flash sale. Suddenly, 1000k orders came. Those arrive within a few minutes. Without a queue, downstream service would receive traffic immediately. Some services might crash, others might become overloaded. With a queue, incoming messages are stored. The queue absorbs the traffic spike. Consumer processes messages at a manageable rate. Think of a queue like a shock absorber in a car. Instead of passing every bump directly to a vehicle, it smooths everything out. Message queue do the same thing for distributed system. Now imagine one email service is not enough. Messages are piling up. What can we do? Simple, add more consumers. Let's follow the architecture. The queue continues receiving messages, but instead of having a single consumer, we now have three consumers. Consumer 1 processes some messages, consumer 2 processes other messages, consumer 3 processes the remaining ones. The workload is distributed automatically. This allows us to scale horizontally. If traffic doubles, we can simply add more consumer. This is one of the reasons queues are so popular in large scale systems. Now what happens if a consumer crashes? Imagine an email service crash. Without a queue, messages may be lost. Emails may never be sent. Now let's see what happens with a queue. The producer places a message into a queue. The consumer starts processing it, but suddenly the consumer crashes. The message remains safely inside the queue. Another consumer can later pick it up and processes it. The work is not lost. This dramatically improves reliability. YouTube uses it. Suppose you upload a video to YouTube. After upload, many tasks needs to happen. Generate thumbnail, create 720p version, create 1080p version, create 4K version, scan for copyrighted content, generate recommendation. Should YouTube perform all these tasks immediately? That would be incredibly slow. Instead, YouTube creates messages and places them in queue. Different workers process different tasks asynchronously. The user doesn't have to wait. The system scales beautifully. Uber also uses message queues heavily. When you book a ride, the system must notify drivers, update location services, record analytics, calculate search pricing, update monitoring system. Many of these tasks happens through message queues. Otherwise, every ride request would become a slow and fragile. Now let's try to understand a popular message queues technologies. There are many queue technologies present as of today. The most common are: first is RabbitMQ, simple, reliable, easy to understand, great for traditional queue-based workload. Then Apache Kafka, built for massive scale, handles huge amount of events, widely used by Netflix, Uber, LinkedIn, and many large companies. We will dedicate an entire lesson to Kafka later. Amazon SQS, managed queue service from AWS. No infrastructure management required. Very popular in cloud native applications. Now, what are the trade-offs of using message queue? Advantages of using message queues are: message queue decouple services, improve scalability, improve fault tolerance, handle traffic spike, allow asynchronous processing, increase system reliance. And what are the disadvantages? Additional infrastructure, more operational complexity, harder debugging, message ordering can become challenging, eventual consistency, messages may be delayed. Now, on message queue, these are the very frequently asked interview question. What problem do message queue solve? The answer is they decouple services and enable asynchronous communication. Next question is, what is the difference between producer and consumer? Expected answer: the producer creates messages, the consumer processes messages. Next question is, why do message queue improve scalability? Because they absorb traffic spike and allow independent scaling of consumers. Then what happens if consumer crash? The message remains in the queue and can be processed later by another consumer. When would you use message queue? Expected answer is whenever work can be processed asynchronously. Example: emails, notification, analytics, video processing, background jobs. Some of the very common beginner mistakes which developers do during implementing queue are: first mistake, thinking queues make system faster. Queues don't necessarily make processing faster. They make system more scalable and resilient. Mistake 2 is assuming messages are processed instantly. Queues introduce delays. Processing happens asynchronously. Next mistake is ignoring messages failures. Messages can fail processing and may need retries. Next mistake is using queues for everything. Some operations require immediate responses and should remain synchronous. Now let's recap what are the things we learned. A message queue is a temporary storage system for messages. Producer places message into a queue. Consumer processes messages later. Queues enable asynchronous communication. They improve scalability, improve reliability, and help system handle massive traffic spike. A message queue acts like a buffer between services, allowing them to work independently without blocking each other, and that's why message queues are one of the most important building blocks in the modern distributed system.